Welcome to the Calculus 2 class. Today, we're gonna study Taylor polynomial. How gonna use Taylor series to approximate value of function like sine, cosine, exponential function. Taylor series represent function as a power series. Taylor series is infinity sum of power. Now we're gonna study Taylor polynomial in this session. So first, explain how to Taylor polynomial approximate a function as a nearer point C, which is center. After that, we construct Taylor polynomial for various degrees for given function. In the end, use the polynomials to estimate the function values and compare accuracy with the original function. What is Taylor series we studied previous session? Give the function and function centered at C, then we find the Taylor series f of x equal fn's derivative of C over n factorial x minus C to the nth power. That's the Taylor series of function f centered at C. Expand this series, right? That's gonna be f of C plus f prime of C over n factorial and until fn's derivative of C over n factorial over n x minus C to n plus keep going, which meaning is, guys, very carefully see, this one is not stop, that's gonna be keep going. This power series, Taylor series, infinity sum of polynomial. How gonna use Taylor series? This is infinity sum. We cannot using this infinity sum of power. So now I'm gonna introduce what is Taylor polynomial. I'm gonna introduce nth Taylor polynomial f of x as centered as C. So here is Taylor polynomial. Pay attention, is n here, guys. Previous slide, I showed the Taylor series of function of f as centered C. So Taylor polynomial is stop and stop right here. Notation wise, here is n. They represent the degree of this polynomial n. Then you're gonna have sum of power until degree n right here. That's what we call nth Taylor polynomial. So we can only use a finite term for the function of f of x. That's what we're going to use to approximate value of function. It's applied to Maclaurin polynomial too. Maclaurin series is going to be Taylor series as center is 0. Nth Maclaurin polynomial, guys, emphasize here. Nth Maclaurin polynomial. That's you have emphasized it. Then Tn and its degree represent nth degree polynomial. Center is 0, start f of 0, the end f nth of 0 over n factorial xn. So focus n represent degree of polynomial. You stopped this polynomial degree n. That we call Maclaurin polynomial. Let's find Maclaurin polynomial T1, T2, T3, for exponential function. So we're going to use Maclaurin series for e to the x to find Maclaurin polynomial. T1 meaning is, here is the exponential function, and Maclaurin series is going to be infinity sum. So expand this series, 1 plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed, infinity sum. That's the series, right? So we want to find T1. T1 is meaning is, guys, degree 1 Maclaurin polynomial. So you're going to take until degree 1. That's the 1 plus x. This is a linear function. Only you take first and second term until degree 1. So let's just sketch the first one. Here is right there. F of x is e to the x, t1x, degree 1 Maclaurin polynomial gonna be linear function. That's you're gonna sketch right here. So that's not even close. So let's take T2. T2 meaning is degree 2 polynomial. Degree 2 Maclaurin polynomial. We're going to take until degree 2 from the Maclaurin series. 1 plus x plus 1 over 2 factorial x squared. That's going to be quadratic function. So let's see how close the exponential function. Now we're gonna sketch degree 2 polynomial quadratic function right here. Getting close except left side, right? Let's find degree 3 Maclaurin polynomial T3. You're gonna take the term until degree 3. So that's gonna be T3. 1 plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed, degree 3 polynomial. That's the degree 3 Maclaurin polynomial. Now let's see, this is exponential function. Sketch the degree 3 Maclaurin polynomial gonna be looks like this. Getting close except this side, which meaning is this Maclaurin polynomial getting close to the exponential function. That's the concept of Maclaurin polynomial. Let's have another example for Taylor polynomial T0, T1, T2 for function ln x. Center gonna be 1. What is T0 gonna be? Here is Taylor polynomial degree n. So we want to find degree 0. What is degree 0 meaning is constant term, right? T0x gonna be f of 1 because center is 1. So we need to find f of 1. Degree 1 gonna be you only take until degree 1. F of 1 plus f prime 1 over 1 factorial x minus 1. T2 meaning is degree 2. So f1 plus f prime 1 over 1 factorial x minus 1 plus second derivative of 1 over 2 factorial x minus 1 square. So let's find T0, T1, T2. We need to find first derivative, second derivative. What is f of x is ln x. So f of x ln x, f of 1 is gonna be 0. ln 1 is 0. So T0 gonna be 0. We need the first derivative. F prime x gonna be 1 of x. So f of f prime 1 is 1. So this one is f of 1 is 0, f prime of 1 is 1. We have 1 over 1 factorial x minus 1, which meaning is t1x gonna be x minus 1. We need the second derivative. 1 of x meaning is x negative 1. Take derivative is f second derivative gonna be negative 1 of x squared. So second derivative 1 gonna be negative 1. F of 1 is 0, f prime 1 is 1, f second derivative 1 is negative 1. So you have 1 of 1 factorial x minus 1 minus 1 of 2 factorial x minus 1 square, x minus 1 minus 1 and half x minus 1 square. That's the degree 0, degree 1, degree 2 Taylor polynomial for ln x. Let's find higher degree Taylor polynomial for ln x. We find degree 0, degree 1, degree 2 Taylor polynomial. So higher degree is more close to function ln x. So let's find degree 3. Degree 3 gonna be, you're gonna take the term until degree 3. So we need to find t3x, f of 1 until degree 3, f third derivative 1, third derivative 1, x minus 1 cube. We find the second derivative gonna be, we already know f of 1 is 0, f prime of 1 is 1, second derivative negative 1. We need to find the third derivative f of 3, third derivative of 1. So second derivative negative 1 of x squared, the other way negative x negative 2. Third derivative gonna be negative 2 x negative 3. Negative make a positive. This one is 2 over x cubed. So you plug in here 1. Third derivative 1 gonna be 2. Now third derivative 1 is 2. 3 factorial meaning is 3 times 2 times 1. Then you can simplify this term. 2 cancel out. You have 1 over 3. So you have degree 3 Taylor polynomial looks like x minus 1 minus 1 and half x minus 1 square plus 1 over 3 x minus cube. The higher degree of polynomial is getting close ln x. Now let's have degree 4 polynomial for ln x. So degree 4 Taylor polynomial means we're gonna take from degree 0 until degree 4 terms, okay? So t4x gonna be f of 1 until f fourth derivative 1 over 4 factorial x minus 4th power. We already know its coefficient until f third derivative 1. So we need to find fourth derivative. So third derivative of x is 2x negative 3. Take a derivative meaning is 2 times negative 3x to the negative 4. When you plug it in there, guys, that's gonna be fourth derivative 1 gonna be negative 2 times 3. So I'm gonna plug in the f fourth derivative 1 here right there. But we already find this one, guys. That's gonna be t3x, degree 3 Taylor polynomial. So we're gonna rewrite x minus 1 and half x minus 1 square plus 1 over 3x minus 1 cube. That's the t3 of x. We find f fourth derivative 1 negative 2 times 3. Then 4 factorial meaning is 4 times 3 times 2 times 1. Then we're gonna simplify. 2 cancel out, 3 cancel out. Now you have negative 1 over 4. So degree 4 Taylor polynomial gonna be x minus 1 minus 1 and half x minus 1 square plus 1/3 x minus 1 cube minus 1 over 4 x minus 1/4 power. We find Taylor polynomial with the degree 1, 2, 3, 4 for the function ln x. So how gonna use Taylor polynomial? We're gonna use Taylor polynomial to approximate ln value. So here is an example, guys. We wanna approximate ln 1.1. So we're gonna use Taylor polynomial to estimate ln function. So let's just start T1, 1, 1. T1x gonna be x minus 1. T2x gonna be x minus 1 minus 1 over 2x minus 1 square. T3x, x minus 1 minus 1 and a half x minus 1 square. You add 1 over 3x minus 1 cube, degree 3 term. T4x, you're gonna add negative 1 over 4x minus 1/4 power. So T1, T2, T3, T4. Now you're gonna find T1 1.21 gonna be, you plug in the 1.21x, this gonna be 0.1. T2 1.21 gonna be 0.95. T3 1.21 gonna be 0.09533. T4 gonna be 0.059531. When you find ln 1.1 gonna be 0.0531. See that T111 is 0.1, T211 gonna be 0.95, T311 gonna be 0.09533, T4 gonna be 0.09531. T4 degree 4 Taylor polynomial almost very close ln 1.1. I'm not gonna show theoretical background about this one, but you see ln is Taylor series. This is Taylor polynomial. We just take finite polynomial to approximate ln function, but already degree 4 polynomial already very close ln function right here. That's we estimate log function by using Taylor polynomial. But here is a trade-off. Higher degree, you have more complexion, but more accurate value. So lowest degree, like T1, T2, is much easier to calculate, but there is a big errors. So it decides how error term gonna be. We gonna take a degree of polynomial. This time we're gonna find the Maclaurin polynomial T2, T4, T6 for cosine x, because we don't have to use definition of Maclaurin polynomial this time, because we know Maclaurin series for cosine. So cosine x gonna be 1 minus x squared over 2 factorial x4 over 4 factorial. That's the Maclaurin series. T2 gonna be, you're gonna take the terms until degree 2. That's the T2. Maclaurin polynomial gonna be 1 minus x squared over 2 factorial. T4 gonna be now this time until degree 4. So 1 minus x squared over 2 factorial plus x4 over 4 factorial. T6 gonna be, you're gonna take a term until degree 6. So you want a more accurate cosine value, you should take higher degree, T6, T8, T10. But when you take higher degree of macroin polynomial, you more complex and take a while to evaluate that polynomial. Let's estimate cosine 1 by using macroin polynomial, guys. So here we find T2 gonna be 1 minus x squared over 2 factorial. T4 gonna be degree 4, 1 minus x squared over 2 factorial plus x4 over 4 factorial. T6 gonna be, you're gonna add one more term, degree 6, negative x6 over 6 factorial. Let's find the T2. This is polynomial, you plug in the number, you can find it. T21 gonna be 1 minus 1 factorial, that's the 0.5. T41 gonna be 0.5417. T6 gonna be 0.5403. Cosine 1 gonna be 0.5403. So already T6 is very close cosine 1. So you have degree 6 macroin polynomial to approximate cosine value. Cosine 1 is infinity series, but we can only use T6 to approximate cosine 1. That's how we're gonna use Taylor polynomial. Let's have another example to use macroin polynomials. So first, we want to find macroin polynomial T4, T8, cosine x squared. What is the T4 meaning is degree 4 polynomial. T8 meaning is degree 8 polynomial. So how gonna find it? First, let's find macroin series for cosine x. That's gonna be 1 minus x squared over 2 factorial plus x fourth power 4 factorial, so on. So we are looking for a macroin series for cosine x squared. X gonna be replaced by x squared. So cosine x squared gonna be 1 minus x squared squared plus x squared fourth power, x squared 6, so on. Now, let's simplify this one first. X squared squared x fourth, x squared fourth, then 2 times 4 is 8. 2 times 6 is 12, 2 times 2n gonna be 4n. So we have 1 minus x fourth power over 2 factorial plus x to the 8th over 4 factorial minus x 12 over 6 factorial. We are looking for macroin polynomial degree 4. So you're going to take until degree 4 terms. So that's going to be T4 over x, 1 minus x fourth power over 2 factorial. How about T8? Degree 8. So you're going to take from first term to the degree 8 term. So that's going to be T8 over x, 1 minus x fourth power over 2 factorial plus x to the 8th over 4 factorial. Now, let's estimate definite integral cosine x squared from 0 to 1. We cannot find antiderivative cosine x squared, so we're going to use macroin polynomial T4 and T8 to approximate this definite integral. So we want to use T4, degree 4 Maclaurin polynomial for cosine x squared. So that's gonna be 1 minus x fourth power 2 factorial. So integral 0 and 1 cosine x squared dx, cosine x squared gonna be approximate 1 minus x fourth over 2 factorial. So now we can find this integral. So what is 2 factorial is gonna be 2. Find the antiderivative 1 minus x fourth power over 2. That's gonna be x fifth over 5, which means x minus x fifth 5 over 10. Plug in the 1 and 0. We find 0.9. So we estimate this definite integral by using Maclaurin polynomial. Now we're going to use degree 8 Maclaurin polynomial. That's T8 gonna be 1 minus x fourth power over 2 factorial plus x eighth power over 4 factorial. So integral 0 and 1 cosine x squared dx. So we're going to approximate cosine x squared by T8, degree 8 Maclaurin polynomial, 1 minus x fourth power over 2 factorial plus x to 8 over 4 factorial. 2 factorial is 2. 4 factorial, 4 times 3 times 2, that's 24. 1 minus x fourth to the 2 plus x to the 8th over 24 dx. We're going to find antiderivative each term. X minus x to the 5th over 10, x to the 9, 24 times 9 is 216. And then you plug in the 0 and 1. This value gonna be 0.9046. So this value, cosine x squared, this definite integral gonna be 0.9046. Now, when you use Maclaurin polynomial, we can estimate definite integral, even though we cannot find antiderivative. What we study here, guys, if we study Taylor polynomial, it is polynomial that approximate a function near a point. Here is key point, guys. Here is Tn degree n, k equal 1 to n. You're gonna add it. The highest degree gonna be n. That's you remember that degree n polynomial. So more term, better accuracy near the center of expansion. But this one is more effort and complexity if you add more terms. Taylor polynomials turn complicated function into simple polynomials that are easy to compute and analyze. So sine cosine x can be write as a simple polynomial to estimate and analyze. So this is application of Taylor polynomial.